Right.
Right. So this is the work that I presented at the Cambridge, the non-dysfunctional programmers meetup last Tuesday on in my experiments with the new GHC's linear types extension. I tried to using that in Clash. So, like when we think about Clash, what we do is we have our function descriptions in Haskell, and they sort of match to this diagram on the right. But what we do is that we map arguments to input ports, and we map results to output ports. But also very importantly, so here we have a full header, which is the composition of two half headers. But what we also do is that if we apply the translation of application is turned into a instantiation of a copy of the circuit corresponding to half header. Right, that's how Clash operates. So to reiterate, function arguments, they become input ports, and functions result become output ports of circuits, and then function application, they instantiate a copy of the circuit corresponding to the applied function, and then applied arguments are directly connected to the input of those ports. However, instantiating a copy is just one of many valid translations that you could actually have from going from a functional language program to a digital circuit. As a quick aside, I'm going to introduce some notations that are just for this presentation. You don't have to include them once you enable linear Haskell or anything. This is just for demonstration purpose for this presentation. So we have this this I that indicates that this argument will become an input port, and this argument will also become an input port, and this tuple will become an output port, and this output, this O, distributes over product type, so you get like two output bits, right? And again, so the way Clash translates things is that if we do function application, that is sort of translated to an instantiation of that of a copy of the circuit. But you don't necessarily have to do that. And for example, Alan Mycroft and Robert Sharp in their SAFL language, they actually by default have only a single instantiation of a function, and function application is translated to in adding additional scheduling logic around the applied function, and then input ports are multiplexed from the arguments from the different locations in which the function was applied, and then it just operates over time. So the way to think about that is where if we do map with some function over a vector that's 8 long, that's going to happen instantaneously. And in their SAFL language, by default, if you do map with some function f, there will only be a single instantiation of f, and it would take 8 cycles to match or forward those arguments or the elements from the vector to those to that single instance of the function, right? And why am I saying this is that the problem that I'm going to solve with linear Haskell is very specific in a way to the way that Clash actually translates Haskell functions to circuits. So one of the problems that we have is, of course, higher order functions, because we said, arguments, they map to function types. Arguments, they map to input ports. But what if we have arguments with a function type? Like, how many bits does this function require, aside from the fact that currently it's polymorphic? But, let's assume it was monomorphic, right? How do we translate application? Because we don't really have something to instantiate, right? So the way that Clash has to solve it currently is through a process called specialization, because basically Clash is a whole program compiler. So what we do is that we basically make a copy of dup, this dup function, and we substitute the applied arguments in all the places where we have a reference to the argument which has a function type. So we get a new function called dup spec that, let's say, this dup specialized on ×2, right? And now from the apex down, or the apex of the function hierarchy, which we call top entity in Clash, right? From the apex down, like the entire function hierarchy is completely first order through this specialization. Dup is no longer referenced from any part from the apex, right? So now we can translate it. But this requires like whole program compilation. But so yeah, what would happen if the apex of our function hierarchy, top entity, is a higher order function, right? And that now there's nothing to specialize, and so we're kind of stuck. Like, oh, what do we do with this argument that has a function type? Well, we know this argument, simple integer, can just become an input port, so many 64 bits, and this result can just become an output port. But what are we going to do with this argument that has a function type? So, the idea that I'm going to discuss now is something that was already discovered and discussed by Dan Gaika in his geometry of synthesis papers, and the way that they work it out is that if you're trying to translate an argument that has a function type, then you sort of do something called polarity inversion, where the arguments of the abstracted function become outputs, and the results of the abstracted function become inputs, right? And by abstracted function, I mean the argument that had the function type. So, first, let's imagine that we somehow managed to specialize our top entity on this function f, then this would sort of be the corresponding diagram, right? We have top entity, and it instantiates a copy of this function f. And we have a, which is our input, and then we have our output over here. So what does polarity inversion, how does that work? And you can see that in the diagram, how it works as well, is that, f will now be instantiated, or could be instantiated, outside of the top entity, right? And then we see that the arguments that we gave to f, right, must now become an output of our top entity, right? So this a plus 1, right, that's an argument to this f, this higher order function. So now that becomes an additional output of our top entity, and its results of the function f become input ports, which we, in case of this top entity, simply forward again, right? So that's what I mean. So now, if we look at this type, so this must become, an output port, because it's the arguments that we're going to pass to f, and the result's going to become an input port. And so this is how we could translate arguments with function types to separate ports and still sort of, instantiate it in the same way. So you might wonder, like, but why would we ever want higher order top entities, right? Or, why would we want to have something at the apex of our function hierarchy be a high order function? Well, basically to have, what I feel is, beautiful descriptions of communication with peripherals. So, let's assume we have a top entity which communicates with two peripherals which are bidirectional, and we have switches, which are, just unidirectional, they're inputs, and we have some LEDs. Then, because of this two-way communication, right, we get the results from the peripheral over here. So we get the results from peripheral 1 over here, and then we pass in this argument over here. If they happen, like unless we use like new type descriptions, we might accidentally switch these two, and the type checker won't catch that, right? It's just kind of ugly. It would be much nicer, if we can just have two peripherals, with bidirectional communication, and we just map them or just model them as functions, right? So we have here just peripheral 1 and peripheral 2, and everything is nice together. And we can just apply the thing. We can never mess up the arguments, right? Well, I guess we can mess up the application, but that's beside the point. And here, everything is more local, and I think it's a far more beautiful description. But here's the catch, and this is where, the linear types come in. Right, we cannot duplicate these peripherals, right? They're outside of our control. Before, with whole program compilation, we could freely duplicate, and again, we duplicate because we're clash, right? Clash duplicates function. If we apply a function, we want to duplicate it. That's how the entire compiler is built. But we can't do that for these, things that are outside of our control. So we must ensure that these two functions are used only once, right? And to demonstrate basically what would go wrong if we didn't, well, so there's like two options. Either some parts that try to reference peripheral 1 aren't connected at all, or we're all connecting them to the same peripheral. And so for things that we're trying to send over to peripheral, there would be 1 because would be bad, because if one line is a 0 and the other line is a 1, you would basically create a short circuit. The other way around is okay, from a physical point of view, right? But everything is still very wrong from a semantically point of view. Like it might accidentally work if you try to send over the same arguments for everyone, right? If they, bit for bit, then you wouldn't get short circuiting either. But if they start to differ, then semantically the circuit will no longer correspond with your Haskell simulation. So again, we must use it at most. We must use it once, or at least not more than once. And so that's where linear types come in. So linear types basically says that a bound variable must be used exactly once. And the X linear types is a GHC language extension that implements this concept. And it does it through annotations on the function arrow. So if we have some function f that has a linear function type, then here, this is how we describe it. So the argument must be used exactly once. And by looking at the code, right, it really feels like, if you try to think of it, at least operational, what does use means is basically if the, right, if f is applied, right, and the result is forced to weak at normal form, then we will have a guarantee that the argument will be forced to weak at normal form as well. And so to be clear, the check that GHC does is, right, it's not on how f is used, right? It's not, but it checks the property of f. So it's a check on f itself, right? And so if it sees that if there's any case where the argument is either not used or would be evaluated more than once, a simple example is if your function is simply if you have an argument a and you do a plus a, then so that means it's duplicated, and so yeah, that will be bad. One thing I do want to note though is that currently, in a way, GHC implements somewhat of a conservative notion. Sometimes it can't analyze at all whether it's used more than once, or and then it just throws an error. And so it's currently like a quite limited subset. Basically, all you can have is like lambda abstraction and function applications. You can't have lead bindings, at least. You can't check linearity through lead bindings. But that's beside the point currently for this thing. So coming back, you might wonder, like, so how does GHC determine that an argument with a function type is used exactly once, right? And so the answer is that when the argument with a function type is applied exactly once, and then when the result of the application is also used exactly once. So that's what it means for a function to be used exactly once. So it must be applied once, and then the result of the application is used exactly once. Now, for our purposes, right, we don't really need the linearity, right? It's more actually, so we actually need something that's called affine typing. So for our use case, our use case is functions must be applied at most once, and actually the result of an application can be unrestricted, right? We can read an output. You can't connect multiple things to an input port, but you can just fan out from an output port. So the use of multiple results is okay, but we can work around this restriction, and it's not really important that we can't drop the function, right? We were interested in using them, so how do we do that? So how do we do this unrestricted use? We introduce this data type u, and then this means so some right, that and it's just a simple wrapper, but what this allows us to do, right, because we sort of evaluate to weak at normal form, like all it means now is that we need to pattern match on u at most once in, let's say, inside of this where clause, but then the thing inside we can have unlimited use, but if we write our top entity like this, GHC will check that peripheral 1 and peripheral 2 are used exactly once, and then so it would work. We can properly, if it type checks, then right, we could translate it to a circuit. We can't build a wrong instantiation of it. Right, so this, I already knew about this existing use case, right, from the paper by Dan Geiger, and I was really interested, like, can we explore this new feature some more? Would there be other uses for linear types in Haskell aside from this, communication with peripherals at the apex of our function hierarchy? I do want to highlight though, like, this was an exploration, and the idea that I'm about to present didn't really pan out as well as I hoped it would. And I'll explain why. So, we often build Mealy machines, right? And they are functions from a current state and a current input to a next state and an output corresponding to the current state and input, right? But this sort of description is overly lax, right? This function, in our descriptions, we have full access to the state. And this is kind of bad because in a way you'll be forced to implement them as all as individual registers. And this could be very expensive, let's say, for a very large state where you might not need access all over the place all the time, right? And so sometimes you just need to have access to a single location. So you would want a RAM-backed Mealy machine that with reads and write ports, right? So how would we do that? We could write, we have some F, and we get the data from the RAM and some input, but then it becomes weird. We have to, it feels kind of weird that we have to provide the read address as the output, and then we get the RAM back, and then we have this write address. That's fine, you know, we're just sending data over, but here's some, you know, there's some direct dependency between the read address and the data that we get from the RAM. So I think, you know, it's much, so not only looking at the type signature, right? Also looking at the head of the function, you know, it's just a lot nicer that you can say, oh, I have a Mealy machine F, and I get a read port, which happens to have a function type, and then some other input, and I provide a write port, and I provide an output. I think this is just a far more beautiful description. And so, of course, we know we can't duplicate, we don't want to duplicate the read port because that would make the RAM more expensive. So we must use this read port linearly, right? So that's all really nice. Right, this is a slide that I included for the Cambridge presentation, which I can skip here, and people that watch it online can just pause the video and read it. So let's say we have a RAM, right? We get a write port, like we get a signal that which sort of maps to a write port, and we get this nice read port, which must be used linearly. And this is where things actually start breaking down, right? We made sure that we consumed it linearly, but we have to also actually make sure that whatever, so we produce something that must be used linearly, which is not really checked in, in linear Haskell's extension, but we'll come to that. So, you know, when we, you know, compose the entire system, right? We have a RAM, we get a write port, and it produces a read port, which we, you know, just using a plective functor, we pass in to this F, and that corresponds to this diagram. But again, right? So, but what if we wrote this? And I've highlighted in red. So now we have, you know, I decided to additionally export the read port, you know, to the entire outside world of the system as well. So now this read port is referenced twice. But that would mean actually that this RAM needs two read ports, you know, they can be accessed independently. But that wasn't our intention of our system at all. We wanted the read port to be used linearly. But sadly, you know, this is not something that you can currently enforce within linear types, at least not while still writing it in this nice, you know, tying the loop kind of way. And this actually manifested itself whilst I was trying to simulate. Because for purpose you can ask me in the during the questions. I actually had to implement the read port using some I/O references because I had to communicate the red value basically from one cycle to the next, but that basically means communicating it from one abstracted function into another abstracted function, and you can only do that basically using I/O refs. And this is fine, right? If you know, so this RD is a function, right? If you know that this function is used linearly, then you know that then we know that this I/O reference is only going to be updated once. So it's, let's say, safe to use the unsafe perform I/O, right? As long as this RD is used linearly. So here we have our system and some program, and this program is there. This is a bit more complicated version of the, you know, the RAM and the Mealy thing we saw earlier. But anyways, here we have the RAM and we have our read port, right? And currently it's used linearly, and it's all nice. We can load it in our machine in the REPL, and and we can run the program. So there's this program here, and it computes the largest common divisor of or the greatest common divisor of 6 and 4, which is 2, and ultimately it stores this in location 8, right? So how do I currently print this output? Well, basically I monitor the write port that we're sending to the block RAM and just outputting the data that's being sent there. And so that's how I get this output. That's not how I started out though. I knew that it was going to be sent over to location 8. So I started out actually like, oh, I'm just going to continuously read location 8. So let's update, let's update, reload it with this updated state, and let me try to run the program again. Like, oh no, what happened? Like, I think there was, it jumped over or it didn't jump, and so like it probably didn't perform this jump or any of these, and it just it ran out of the end of the program. So something actually went wrong because I didn't use the read port linearly, right? And now it works again. Okay, coming back. So, again, right, so linear types, the concept is about, bound variables being used exactly once. But linear types actually only checks lambda abstracted variables, right? It checks the linearity constraints on the arguments of functions. Like I might have been able to create an API for the RAM, which is sort of based on either something like CPS or the ST trick with some, with some rank 2 types. But then it becomes weird because basically the RAM would then take a function that takes a read port and then takes a continuation, but this continuation must be in some rank 2 state, because otherwise I can just provide the identity function to the RAM and I would immediately get the read port back, and you don't want that. Anyways, I tried some tricks and I think it could be done, right? So that's why I'm saying it's hand wavy here. I think it could be done with the current API or with to make sure that the read port is only used once, but then you can't get this nice looking description anymore. I bet you can't have your cake and eat it too, in a way. So how do I envision it might work? And there's, lots of things that still need to be worked out and it's really not complete. But it would be really nice if I could say, instead of, so normally, if I have this &1 on the left-hand side, then linear types checks that RAM will consume its argument linearly. And so my idea is to put the &1 on the right-hand side of the arrow. And that says that, whoever uses RAM must use the result produced by RAM linearly. And then I also have this sort of idea for a linear let binding, right? That, that doing it like this will satisfy the type of RAM, right? And then this read port, because it now will be referenced in 2 places, and this is like a linear let binding. This will now fail to type check because it's referenced twice, right? That this is my harebrained idea, right? There's probably lots of things that would need to work out, but this is not implemented at all by the linear types extensions. So to conclude, right? There's basically multiple ways to translate function application to a circuit, and the one that we picked, right, means we needed linear types and this inversion of polarity if our functions are instantiated, or if we translate function application to instantiation of a copy, right? Because if things come from the outside, we can only instantiate them once. What is nice is that we can use linear types right now for the peripherals example. I tried to explore using more linear types, and it it worked really well in a way, up to the point that it didn't, right? So like maybe we could add some checks to clash to do the let's say the demand side linearity, right? Or the result side linearity, whatever you want to call it. But that's not there yet in X linear types, the extension, but it might be. So yeah, I'm I think, and there might be many more uses for linear types which I just haven't discovered yet, or people haven't, or other people. I'll post the example that I made for the RAM online for people to check, and that's it. I'm ready to take some questions if there are any.